We are going to solve exercise 1 from probability models set of problems. It says, let x be a random variable such that a, if x follow a binomial distribution like the one we can see here, we have to calculate probability that x is equal to 12 and the probability that x is smaller than 2. So let's start. So in part A we have this binomial distribution, and to calculate the probability we are going to use this statement. As you can see, we have replaced the values and we get that this is our result. Now we are going to calculate the probability that x is smaller than 2. We know that this is equal to the probability that x is equal to 0 plus the probability that x is equal to 1. So, as we did in the previous part, we are going to do the same procedure. Now have a look, we have already replaced the values, and following the calculus with the calculator, we got that this is equal to 0.3342. So here we have our result. Now let's continue with part B. So now in this part we are asked to calculate the probability that x is smaller than mu minus 2 sigma. So first of all we have to calculate mu, that is the mean, and sigma, that is the standard deviation. Applying the properties of binomial distribution, we can see here the formula of the mean and the formula of the variance. So now we are going to replace the value we know and we get the mean. So n is 25 and the probability is 1 divided by 5. This is equal to 5. And this is equal to 25 times 1 divided by 5 times 4 divided by 5. And this is equal to 4. As we are looking for the standard deviation, we have to just make square root to 4. So we know that the standard deviation is equal to square root 4, that is 2. So now that we have our result, our previous result, we are going to replace both of them here, and we get that this is equal to the probability that x is smaller than 5 minus 2 times 2, that is 4. So this is equal to the probability that x is smaller than 1. So as we did in previous part, we are going to make this in part. That's it. The probability that x is smaller than 1 is equal to the probability that x is equal to 0. So using the same procedure as before, this is equal to 25 over 0 times 4 divided by 5 raised to the power of 23. So, following the calculus, we get that this is equal to 0.003778. So here we have our result. Now let's continue with part C. So here in part C we have a binomial distribution with the values n and p unknown. So we have to get the value of p to maximize the variance. Here we have the expression of the variance in a binomial distribution. So if we follow algebra, we get that this is equal to n times p times 1 minus p. So q is equal to 1 minus p. Following again the calculus, we get that this is equal to n times p minus p squared. Okay. So again, following the algebra, we get that this is equal to n times p minus n times p squared. So this is the expression we have to maximize. To do that, we are going to use derivatives. So here we have the first derivative, and to get the value of p, we just have to equal it to 0. So following the calculus, we get that n is equal to 2np. So what we want to know is the value of p. So if we work out p, we get that this is equal to n divided by 2n. This and this disappear, and we get that it is equal 1/2. So now we just have to check that this is a real maximum. To do that, we do the second partial derivative. So this is equal to minus 2n. And as we know that n is the number of experiments, we know that n is always positive. So this is going to be negative, always. So we can say, yes, it's a maximum. So the value that maximizes the variance is a probability of 1/2. This video was recorded by María José López Martínez in the academic year 2012-2013. Thank you for watching.